All right, what's up, pre-calculus? We are going to look at some polynomial functions and really just focus on learning as much as we can from something called their leading term. So let's get into this. A polynomial function, here's an example of one right here. They have non-negative integer exponents on the variable. So just to showcase that, here's an example of something that is not a polynomial. We have a 1/3 exponent, that is not an integer. We have a -8 exponent, and that is not positive. So for various reasons, this is not a polynomial function. What we're going to call the leading term is the term that has the highest exponent. So as I scan through the terms here in this polynomial, I happen upon 5 as the highest exponent, and I will record -7x to the 5th as the leading term. Okay, the degree, let's remember what that means. That is just, well, identify the highest exponent. So we will just record a 5 here. That is a 5th degree polynomial function. Leading coefficient is the value in front of x to the 5th, and that will be a -7. And as you hopefully remember from Algebra 2, the end behavior, how the left end and the right end of the function's graph point, they all are determined by the leading term. And of course, I do hope some of you recall our little even, odd, that we can help to identify where the tail ends of a polynomial function point. And just remember, when the leading coefficient is positive, the right end points up, and when the leading coefficient is negative, the right end points down. So with that in mind, let's just kind of put that in a little summary here using our limit notation. So we have the 4 cases: positive leading, even degree, negative leading, even degree, and of course then we have the odd degrees. So what I'd like to do is maybe handle the first guy for you and maybe ask you to fill in the rest, but should be light work, okay? I'm going to highlight the left end in blue, and I see as the x values approach -infinity on the left, the y values are pointing upwards forever. They will approach positive infinity. For the right end, which I will color code in red, the limit as x approaches infinity, that's our clue for the right side. I see the y values pointing very drastically up, and I will identify that limit as infinity. Could you please pause the video and fill out the next 3? I'll catch up to you in a moment. Welcome back. Let's see how this all played out. So for the second one, I do see that both left and right end point down, so I've recorded that there. When we switch to the odd degrees, remember we know the 2 ends point in opposite directions, and again, I've just recorded the proper type of infinity for each limit. So we're going to extend this not just to power functions, but really let's remember that the end behavior is determined by the leading term, even if there are extra terms floating around in that polynomial. So for something like number 1, let's do a couple things here. We're going to state the degree and leading coefficient of each polynomial, and then we will describe the end behavior using that limit notation. As we look through here at number 1, yeah, that right there is my leading term. And from that leading term, we can identify the degree. Highest exponent is a 5, and the leading coefficient, I'll abbreviate that here as LC, that will be a -2. So let's think about that. Degree is odd, leading coefficient is negative, and you might start to feel your arms pointing in this general direction, and that would be how the ends of our graph will point. Huzzah! All right, let us record that in our limit notation. So for the left end of it, Let's jot this down. We say the limit as x approaches negative infinity of f of x, and we see the left end will point upward, so we've got the infinity. And for the right side, the limit of f of x as x approaches positive infinity, well, we see the right side points down. So that was not a very terrible example. We were very easily able to identify the leading term just by scanning through for the highest exponent. Unfortunately, in number 2, the function is not presented in a simplified form, so we are going to have to bust out our favorite 4-letter F word, FOIL, and start simplifying what we see here. So I'll keep the x squared for last. 5 times 1 is 5. Then we'll have minus 5x minus 3x and plus 3x squared. All right, I will clean up what's inside the parentheses, maybe start to put these in order of highest exponent down to lowest. So I'll start with positive 3x squared minus 8x plus 5. And lastly, I will distribute through x squared by everything, and with a little bit of effort, we do happen now upon the simplified version of the polynomial. And I know the secret to the end behavior lies in the leading term of 3x to the 4th. So, could you please pause the video and write down for yourselves what you believe the leading term, leading coefficient, degree, and end behavior with limit notation should be. Alright, welcome back everybody. Let's see how this played out. So for a degree with 4, leading coefficient positive, 4 is even, we should realize the two ends of this point up, and we can write that limit out for the left side and the right side. Now, just as a little side comment here, this wasn't so tough to simplify, but there could be other functions that could be pretty brutal to work all that out just to get to what we need there, the 3x to the 4th. So as a shortcut, if you're only looking for the leading term, one way to kind of just hone in on what you need without all this extra fluff of the extra terms here would be just multiply together the parts of this function that contain x. So we'd be multiplying together x squared with negative 3x with negative x, and if we play that all out, we would very quickly hone in on 3x to the 4th. All right, let's see what the other side of this page has in store for us. And just wanted to pause for a minute while we are talking about polynomials and address some graphs that are not polynomials. Let's remember polynomials are continuous everywhere. Their domain is negative to positive infinity. So for example, we have a piecewise function graphed here. It's got a little jump discontinuity, not a polynomial. We have a rational function here. It's got an infinite discontinuity where x can't be 0. These are coming up in our future. Get used to that shape, everybody. But it's not a polynomial. And we have an absolute value function here. It is continuous, but it is clearly going to have a different feel to that function. Okay, last thing we want to do here together is just be able to quickly determine some features of polynomial functions based on their degree. If a polynomial function of degree n greater than or equal to 1 could have a maximum of n distinct real zeros and one less than n minus 1 turning points. Now that seems a little abstract, but perhaps we can use these little sample graphs down here to make sure that we get what that's trying to say. So let's think about a quadratic function. We know that is degree 2. And the way that this particular function is drawn, yes, there are two distinct differently located x-intercepts of the graph, which means this quadratic function that I'm showing you does have two distinct real zeros. That's the most number of real zeros it could have. We know from experience there could be another parabola out there that maybe just touches the little x-axis at one location, would have one distinct real zero. It's also possible for a parabola to never touch the x-axis and have no real zeros, but the most you could have is 2. And the number of turning points where we switch from increasing to decreasing or vice versa, that would be a turning point, TP, would be 1 less than the degree, so that would be a 1. For the following 3 functions, could you please try to identify the degree, the maximum number of real zeros shown, and the number of turning points? I'll catch up to you. Alrighty, welcome back everybody, and just to share these out with you, we do see for a cubic function, degree is 3, the maximum number of real zeros we can have is 3, and this graph highlights that for us, 1, 2, 3, and 2 turning points on this cubic function. Here's 1 and here's 1, a relative max and a relative min. All right, quartic function, that's going to be your degree 4. We do see on this graph 4 real zeros. There could be less depending on how the waves turn. 3 turning points on this particular graph. Lastly, we're going to look at the quintic function, that is degree 5, 5 real zeros, and 4 number of turning points, 4 maximum turning points. So that is your rundown of how to use the degree, the leading coefficient, and the leading term to predict end behavior of a polynomial function, and we will look at some more examples when we come back together. That's it for now. Ta-ta!